So what we're going to do for the next 45 minutes or so is talk through an overview of novel protein ingredients for infant milk formula, focusing first on a kind of an overview of consideration in formulation of dairy-based infant milk formula, and then talking in quite second part, talk in more detail about some hopefully interesting work we've been doing on isolating some novel ingredients for infant milk formula. And a lot of this is based on the work of a student of ours, Shane Crowley, who's just finishing his PhD. So the later part of this webinar will be based on Shane's PhD work. I hope everybody can hear me, but if anybody's having difficulty, please let us know in the chat box, or Jenny, feel free to interrupt. And thanks again to Jenny for organising this, for setting everything up. We were delighted to get the invitation, and we're very pleased to have the opportunity to speak to you, as it were, this morning, to you all this morning. So, how this is going to work is I'm going to kick off for the first maybe about 10 or 15 minutes with a bit of an overview and an introduction to infant milk formula and protein, consideration term proteins, and then I'm going to pass over to Seamus. So we're going to kind of double act as we go. So obviously, as people are aware, what we're interested in is trying to consider how to compare and how to modify the composition of bovine milk effectively so as to more closely replicate that of human milk. And that's the whole function of infant formula. But if we go to any basic consideration of the two types of milk, we see that while there are quite a number of similarities, there are some pretty profound differences as well. So, for example, while the total solids and fat levels are pretty similar, pretty much everything is different. There's for example, much higher carbohydrate content, lactose and oligosaccharides in human milk, while conversely there's a much higher ash content in bovine milk. But what our focus today is going to be is to focus on the protein components, because for a start there is a lot more protein in bovine milk than there is in human milk. But critically, the mix of proteins in human milk is quite different to that which is found in bovine milk. So where we're used to a 80-20 or 75-25 ratio of casein to whey protein in bovine milk, in human milk the ratio is flipped, and we have a whey protein dominant system. So we can see that if we're trying to mimic the composition, even approximately, of human milk in an infant milk formula, we have to reverse proportions, change proportions of a lot of ingredients, and where we want to look in particular today is what we have to do to the protein fraction. So just moving on a little bit, because as the title of the webinar indicated, the main focus for today is going to be on proteins, to dive a little bit deeper into the two species, as it were. As we said, the bovine milk has a lot more proteins, but if we look at the makeup of that protein fraction, we see a lot of difference. While, as I said, in the caseins are the dominant protein fraction in bovine milk, they're the minor protein fraction in human milk, and the mix of them is different. Alpha S2 casein, for example, is not thought to be found in human milk, and beta casein is very much the dominant casein in human milk. The other fraction, the whey proteins, there are two major whey proteins in bovine milk, beta-lactoglobulin and alpha-lactalbumin, whereas in human milk, the beta-lactoglobulin is absent, and we have a profile which is dominated by alpha-lactalbumin with much higher levels of lysozyme, lactoferrin, and other whey proteins in human milk. In both cases, casein is found in micelles, but while there is a lot of understanding of the properties of the micelles in bovine milk, the human micelles, which are much smaller, casein micelles in human milk are much smaller, and properties are less well defined and understood. Particular interest of ours in Cork over the years has been not just the proteins, but the enzymes which are present, which break down the proteins. And plasmin is the main one. Plasmin is a blood-derived protease which is found in milk, which is active in every raw milk sample to break down beta-casein. And it is the dominant protease activity in both types of milk. And I'll mention in a couple of minutes why plasmin is interesting. We have done quite a bit of work in recent years, and I'm not going to dwell too much on these slides, but this is a profile, if you like. This image is what's called a two-dimensional electrophoresis gel of milk proteins, and it illustrates quite simply the difference between bovine and human milk when I look on to the next two. If I can take the pointer here, we can see what this is basically a two-dimensional plot of the weight of proteins versus their isoelectric point. And we see a very characteristic, each of these spots represents one of the proteins present in this case in bovine milk. So we have a kind of blotch here in the middle, which is comprised of the alpha caseins and beta casein. We have a trail here of different glycosylated forms of kappa casein, and we have a spot for beta-lactoglobulin and a spot for alpha-lactalbumin, and we've got some higher molecular weight whey proteins. And that's kind of characteristic. If we run bovine milk samples on these kind of gels, we'll see this or a variant of it or something very close to it repeatedly. However, so to human milk, the picture is very different. We get a lot more high molecular weight whey proteins. We get a lot less activity in this middle zone, which corresponds to casein, although we do see the kappa casein. And notably in the whey proteins, we just see one big presence, which is the alpha-lactalbumin. So, in other words, the picture, just taking this as one example of how we can depict it analytically, the picture when I compare bovine and human milk are very different. So if we think it's not just a question of adjusting the total protein level when we consider making different milk formula, but increasingly we're interested in looking at the detail of what exactly is present. And I guess it's how to tailor more specifically protein ingredients to really make these profiles line up more closely is what we're interested in talking about this morning. So how do we bring the two closer together? Obviously, infant formula is a very broad and complex product category. It exists internationally in a lot of different formats, whether it be powders, whether it be Tetra Briks or plastic bottles into which typically the product has been filled after UHT treatment, whether it's retort sterilized in glass bottles, for example, or whether increasingly it's being found in formats such as tablets, etc. So infant formula is complex, not just from the formulation aspects of what we put in, but also the technological aspects. And I'll talk a little bit in a minute about the different families of processes we can use to derive these. But I suppose it's worth noting that as we start thinking about protein ingredients, maybe just to flag that one of the key considerations is going to be we're going to need proteins which ultimately have a range of functionality, whether it be heat stability to retort sterilization or lack of likelihood of fouling in the UHT heat exchanger, or ability to contribute to good reconstitution rehydration properties, for example, in powder. Because if we think about infant formula, it's good to be when in powdered form, reconstituted readily under fairly standardized domestic conditions. So the technological requirements for ingredients for infant formula, among other things, are another complexity of the topic. If we look at a broad spreadsheet, flowchart of how infant formula is typically manufactured, we start to see some of the complexity, I suppose, starting on the left-hand side in the box with all the possible ingredients. And one of the features, needless to say, of infant formula, which isn't surprising, is the length of the ingredient declaration on any container of infant formula. And we can see a list, and probably not even a full list, of all the possible ingredients which can be added to infant formula. About half of the ingredients on the list, like skim milk powder, whey protein concentrate, demineralized whey protein isolate, milk protein concentrate, milk protein isolate, are protein-based, also lactoferrin, beta casein, and high alpha-lactalbumin whey protein concentrate. And I guess we're going to focus this morning on the protein ingredients. Needless to say, a lot of the ingredients on the list are going to be non-proteins, whether they be oils, which are selected to give us the right fatty acid profile, carbohydrates, be they lactose or perhaps oligosaccharides, vitamins, minerals, prebiotics, probiotics, nucleotides, obviously the nutritional requirements of neonates, and at different stages make this a very complex proposition. Then, as the flowchart indicates, there are a number of routes of manufacture, whether there's wet blending of ingredients, followed by heat treatment, homogenization, and then either in container or UHT processing to give us the ready-to-feed formulations in the glass bottles of Tetra Briks or plastic bottles, or whether we evaporate and spray dry to give us powder, or else we dry blend or partially dry blend in some of our ingredients to give us our dry product. So this flow chart again illustrates the complexity of the processing proposition that's ahead of us, and that the requirements, as I mentioned already, for ingredients to be stable to processing propositions throughout the flowchart. If we think about, so if we focus as we will for the rest of our talk on protein ingredients, just a few of the key points again. First of all, they need to be whey protein dominant, that our ultimate formulation needs to end up at a situation where we've at least 60% of our protein present as whey protein. I mentioned at the start that there's a different mineral profile, and this is quite a critical prospect when it comes to protein proposition, that we need to think about either reducing or tailoring the mineral content and making sure that our protein sources don't bring excessive minerals, they don't bring the wrong sort of minerals as it were with them, like, for example, through the use of demineralized whey. If we think about what might happen increasingly in the future, then as we mentioned, human milk is no beta-lactoglobulin, whereas in bovine milk, and therefore in bovine milk-derived protein ingredients, there's going to be a mix of alpha-lactalbumin and beta-lactoglobulin. So we may want to increase the ratio of alpha-lac to beta-lac, or even avoid adding beta-lac entirely. And we'll talk towards the end of this session about some work that's been done on the significance of that for the processing of infant formula. We want to think, again, as we mentioned at the start, human milk is beta-casein dominant, so we might think about altering the ratio of caseins, in particular increasing beta-casein. And again, that's going to be one of the main focuses of our session today, is some work we've been doing on how to increase or purify beta-casein for use in such ingredients. And then just as two final comments, we want to have a good protein quality in the ingredients that we produce, low levels of non-protein nitrogen, for example, and a situation which is particularly of interest, certainly in Europe and in Ireland at the moment, is the fact that a lot of our whey-derived ingredients come from cheese making, and a lot of cheese making, for example, in Ireland, is of coloured cheddar cheese, including annatto, and there's increasing regulation and discussion about the avoidance of the presence of colorants such as annatto in whey-derived ingredients, which are destined for infant formula. So again, just a bit of a scene setter to kind of set the scene for some of the considerations that underpin the kind of work we're talking about. One of the final points I'll make before I hand over to Seamus is the goalposts keep moving. I suppose that the study of human milk is at the moment a fairly active research, and I guess, you know, as with many areas of research, as time goes on, we understand more about the topic, and in particular, we're able to bring more and more sophisticated tools. For example, the two-dimensional electrophoresis I showed a minute ago was something which wouldn't have been available or applied even 20 years ago to milk studies. And once we started using tools like that, we began to realize there were levels of complexity to proteins that we never even understood. So proteomic tools in particular really helped us to learn a lot more about proteins, and maybe illustrated further the depth, the scale of the challenge that we sometimes have. Just to mention one example of how, as time goes on, we've understood more about what we're trying to do, and that's driven some of the considerations. We did some work a number of years ago, which we published in Cork, about comparing preterm and term human milk, and in particular comparing protein profiles. And without getting too much into the detail, I'll just next slide show a little bit, I guess, the key point. First of all, maybe on the right hand side, these kind of bar chart barcode type images are a different type of electrophoresis. Each of these profiles represents the protein profile of an individual mother, and we had a sample of term mothers and preterm mothers. And one of the points was there's quite a bit of variation and variability between the mothers in their specific protein profile, which is something quite notable, the high variability from mother to mother in proteins. But what we're interested in particular was the difference between the preterm and term. If we look at the plots on the left-hand side, basically in the preterm milk, we found that there was a lot more nitrogen present than in the term milk, and there was a lot more activity in the lower plots of an enzyme called plasmin, which I mentioned a couple of minutes ago. And what I said is that plasmin is an enzyme which comes from the blood, which breaks down protein. So what was very interesting in this study was it showed to us that there's a lot more nitrogen in the milk of some mothers of preterm infants, but there's a lot more enzyme activity, which is breaking down, for example, these cases which is present. So the protein profile had changed quite a bit, and there's quite a lot of proteolysis going on in the milk. Now, so this again illustrated part of the complexity, and it led to a kind of a long-standing interest in Cork. We have, I guess, parallel research programs going on, one on proteins in infant formula and formulation consideration, and the other is on human milk. And we have a large longitudinal study of a much larger cohort of term and preterm mothers, with 70 mothers currently having completed the study, where we're doing a lot of work on the proteins and biochemistry of that milk. So that's been very interesting work we've been doing in Cork. So for now, what I'm going to do is I'm going to pass over to Seamus, who's going to take over the next part of the talk and talk you through some of our work on how do we address some of these challenges in terms of formulating new protein ingredients. Okay? I hope that's been clear and audible critically to everybody. And I'm happy, Seamus, are you happy to take over from here?
Yes, indeed. Thanks very much, Alan and Jenny. I hope everybody can hear me. If not, I'm sure we'll see some text popping up in the chat box if people are having any difficulties. Okay, so picking up from where Alan left off there, on human milk and the importance of it in developing the formulations for various types of infant nutrition products. We've felt that it was useful just to give a brief overview of the different types of infant nutrition products, and just to show where the focus for the remaining work covered in this presentation lies. So a lot of what we'll be talking about around modifying casein protein profile and whey protein profile for infant nutrition applications will actually be focused on what we call the first stage category of infant nutrition products. And this basically represents the first products for the first 6 months of life, essentially. And I guess the reason for focusing on that particular category is that human milk is the blueprint for the formulation of those types of products, and they're nutritionally complete. They tend to be the more complex products, and they're also lowest in protein compared to, let's say, second, third, and fourth age infant nutrition products. So it can be quite challenging to formulate these particular products. But just to say that while the focus is on first stage for the first 6 months, some of this information is also relevant, obviously, in the older age category products, such as follow-on formulas and growing up milks, and in particular in some of the specialty products as well. So I'm just going to move on the slide, and hopefully everybody is with me. And Alan has mentioned some of this already in terms of the ingredients that are used in infant formula. There's a table given here on the next slide, which categorizes some, it's certainly not an exhaustive list, of the ingredients that are used in the formulation of infant nutrition products. And I guess our main focus for the purpose of this presentation is on the protein-based ingredients. Okay. Now, what you'll see at the top of the list here is skim milk powder, and that obviously is the backbone of many early stage infant nutrition products, because it contributes all of the casein, some of the whey protein, and quite a bit of the minerals as well. I guess it's obvious to most people, but the reason it's skim milk powder and not whole milk powder is that it allows the formulators the opportunity to blend typically vegetable oils then to best match the fatty acid profile of human milk. And any additional carbohydrate that's required in the form of lactose is typically added in as a lactose ingredient. And of course, to bring up the whey to casein ratio to meet that 60% of the total protein being whey protein, to meet that target, whey proteins are typically added to first stage infant nutrition products in the form of demineralized whey, since that was made possible with demineralization technology in the 60s. And in some products, that may also be achieved by adding ingredients such as whey protein concentrates or whey protein isolates. Now you will see whey protein isolate and milk protein isolate on the list there, but these, I guess, are typically used in the manufacture of lactose-free products, where it's desirable to have the casein or the whey protein component without the lactose component. And those products are typically filled with maltodextrin or corn syrup solids or dried glucose syrups as the carbohydrate sources then. So skim milk powder and demineralized whey would be the main high volume protein based ingredients that are used to achieve the casein to whey protein ratio in these first stage infant nutrition products. What you will find obviously on the list as well is hydrolysates, so casein and whey protein based hydrolysates, and they're added or can be added for reasons that Alan mentioned earlier, where it's clear that the proteins are, particularly in preterm milk and early stage infant nutrition products, or human milk, that the proteins are at least partially digested. So the hydrolysates can help in that regard, or also where it's needed to have a hypoallergenic product, where the proteins will be extensively hydrolyzed. I guess over the last 10 years or so, and the time frame varies depending on the geography, but there has been quite a bit of development in specific protein fractions for use in formulating infant nutrition products. And one of the ones that you see on the table there is alpha-lactalbumin enriched whey protein concentrate. And this obviously is an ingredient that was specifically developed for the formulation of infant nutrition products, whereby it is a WPC, typically a high protein content WPC in the region of 70 to 80% total protein, of which the alpha-lactalbumin fraction is specifically enriched. And we'll say a little bit more about that later on. Alpha-lac, I guess, is one of the major whey proteins in human milk. Therefore, it's desirable to enrich it in the manufacture of infant nutrition products. Also on the list there is lactoferrin, and clearly that's an important product, or protein. Typically, it can account for 10% or so of the total protein in human milk, with the levels being much lower than that in cow's milk. So its enrichment is desirable. And beta casein is one of the protein ingredients that we're going to spend most of the time focusing on for the remainder of this presentation. And I'll say a bit more about that in later slides. But just on the lipids for people that might be interested, I mean, typically what happens is that a blend of individual vegetable oils is prepared such that the fatty acid profile of human milk can be matched. On the carbohydrate side, as I mentioned, typically in first stage infant nutrition products, most if not all of the carbohydrate is lactose. Sucrose normally would not be used in the early stages, but only for later stage growing up milks and toddler milks and so on. And in those products in the later age category products, and maltodextrin and corn syrup solids can also be used. Two important ingredients which are used quite a bit obviously in first stage and follow-on infant nutrition products are fructooligosaccharides and galactooligosaccharides. But that's as much as we'll say about the lipid and the carbohydrate components for the purpose of this presentation. Okay. So just coming back to beta casein then, there are a number of individual casein fractions within milk, within cow's milk and also human milk. And in the case of human milk, I guess one of the unique aspects is that the vast majority, as you can see from the table there, highlighted in yellow, the vast majority of the casein, the 40% of the total protein that is casein within human milk, is actually beta casein. There's very little alpha. It's 1 casein. There's essentially no alpha. It's 2 casein, and there's some kappa casein. So from a formulation point of view, the main casein of interest in making infant nutrition products is beta casein. And if we were to use cow's milk based ingredients, so skim milk powder, or milk protein concentrates or isolates, then we don't modify that level of beta casein, and we use the innate level of beta casein that's present in the cow's milk derived ingredients, with no modification to the beta casein to alpha S casein ratio. The whey proteins, we'll come back and talk a bit more about those later on in the presentation. But again, even within the whey protein component, certain whey protein fractions are more desirable than others, and you can see highlighted in yellow that alpha-lactalbumin is the dominant whey protein fraction within human milk. And in fact, there's no beta-lac, as Alan mentioned earlier, there's no beta-lac in human milk. So again, from the point of view of designing, tailoring whey protein-based ingredients, the objective would be to remove beta-lac and enrich alpha-lac, and ideally to have significant levels of lactoferrin in there as well, given the fact that it's quite an important protein in human milk. So there are just some of the, I suppose, overarching desires from the point of view of matching the individual casein and the individual whey protein profile of human milk in infant formula. So these are the drivers of much of the work that we've been doing then. Okay, so on the next slide then, the case for enriching beta casein. This, even though there are big differences in the casein profile, it hasn't received, I guess, a huge amount of attention from the point of view of development of ingredients. Certainly not to the same extent as the efforts that have been put into matching the whey protein profile of human milk in infant formula in recent years. And this is reflected in the fact that, there's a very small number of industrial scale manufacturers of beta casein, and there have been a number of processes proposed and researched and developed and so on, and they each take different approaches, which we'll say a little bit more about later on. But the particular approach, I suppose, that we've taken in recent years, based on some work in collaboration with the University of Wisconsin in the US, is to use a membrane filtration based approach, which essentially exploits differences in the equilibrium of beta casein between the micellar form and the monomer form as influenced by temperature. So it's purely a physical size based separation, having exploited the chemistry of the proteins and the ability of the proteins to associate just using differences in temperature. And you can see a reference at the bottom of the slide there to the process that we've patented in recent years as well, and let's say a bit more about that later. So if the objective then, which it has been for us in recent years, is to enrich, fractionate the caseins and enrich the beta casein fraction in particular for the development of infant nutrition products, then you can see on the next slide, from the point of view of producing casein-based ingredients, we have a number of different options available to us. And the first is probably the more traditional one, which is where we take skim milk and we precipitate the caseins. Destabilize them and precipitate them in the manufacture of ingredients like rennet casein, acid casein, or co-precipitates. And they're important ingredients, and they're highly functional ingredients. But one of the challenges, I guess, from the point of view of infant nutrition products is mineral profile, but also the fact that most of these ingredients are not soluble, which does limit their application in the likes of infant nutrition products. An alternative then to manufacture casein enriched ingredients but maintain them in the soluble form is to make ingredients like micellar casein concentrates and milk protein concentrates. And these obviously are enriched in casein, and some of the minerals have been depleted. But I guess what doesn't change is the ratio of the individual caseins. We're basically enriching all of the original caseins in the proportions that they would have occurred naturally in skim milk. So our approach then has focused on the fractionation of individual caseins, particularly beta casein, for reasons of wanting to include it in next generation infant formula products, certainly, but also just to mention that there are a number of other very interesting physicochemical and even nutritional functionalities associated with beta casein as well, which we won't go into during the course of this presentation, but it is a very surface active protein as well. So a lot of work is being done at the moment across the world in the areas of foaming, emulsification, encapsulation, and targeted delivery applications using beta casein as a functional food ingredient. So our work was focused on, as I say, on membrane-based fractionation of the individual caseins, exploiting differences in the association of the proteins based on temperature. And that means basically taking, in practice, what it means for enriching beta casein is to take skim milk and cool it to typically to temperatures of between 4 and 8 degrees Celsius. And under those conditions, quite a bit of the beta casein dissociates from the micelles. And that dissociated beta casein is monomeric. Okay, so it's free beta casein present in the serum phase of the milk. And probably one of the questions that will pop up later is how much of the beta casein dissociates. Typically about 15 to 20% of the total beta casein is what's dissociated on cold storage of skim milk. And what we do then is we take that cold dissociated skim milk and pass it through a microfiltration membrane at low temperature as well. And the objective of that is to strip out the whey proteins plus the dissociated beta casein into the microfiltration permeate stream. So we're literally just using physical size-based separation to fractionate the beta casein in the permeate fraction from the micellar casein, which is retained then in the retentate fraction. So it's similar to making a milk casein concentrate essentially, except that a fraction, typically between 10 and 20% of the beta casein, is recovered in the permeate fraction. So that permeate fraction then it's a clear solution at low temperature, and it contains native whey proteins. It's often referred to as an ideal whey stream or a milk serum stream, and it contains the beta casein. So that's an important starting point in the manufacture of these types of ingredients. And just on the next slide, then it's actually a photograph of the lab scale membrane filtration unit that we would have used at UCC for a lot of this initial work, whereby we have membrane cassettes of 0.1 meter squared surface area with different porosities, which was the focus of the early stages of this work. Following the early stage work, then quite a bit of this was scaled up in the pilot plant and in Madison, and also at our collaborators in Teagasc Moore Park in Ireland as well. So just to give you a flavour of some of the work that was done in this area, you can see highlighted on the slide there is microfiltration membranes of two different porosities, so 0.1 or 0.45 micron pore size microfiltration membranes. Again, just to mention that the majority of this work, for those coming to this presentation from a membrane background, most of this work was done using polymeric membranes, with a small amount in the latter stages done using ceramic membranes. So just moving on the slide, just to give you, I suppose, an idea of the protein profile and the importance of the protein profile in these permeate fractions. When we generate cold microfiltration permeate using 0.1 micron microfiltration membranes, what we end up with is, as I mentioned earlier, this clear permeate stream, and you can see a photograph of it given on the slide there. It's whey protein dominant, with the main non-whey protein component being beta casein, and you can see that shown in the middle lane on the gel on the right hand side as well. So you can see a single band corresponding to beta casein in the middle of the gel, and then the two major whey proteins towards the bottom of the gel, beta-lac and alpha-lac. And this is basically the starting material for the production of these next generation infant formula ingredients containing native whey proteins enriched in beta casein. But just to mention the influence of porosity of the membranes, when we use membranes with a larger pore size, 0.45 micron membranes, we ended up with quite a different material. As you can see shown in the photograph there on the slide, it's an opaque, turbid, permeate stream. It does still contain the native whey proteins, beta-lac and the alpha-lac, but as you can see from the gel, it contains a lot of the other caseins in addition to beta casein. So alpha S casein is in there and kappa casein is in there. So essentially what's present in that permeate fraction is small casein micelles. So we've selectively fractionated the smaller casein micelles into the permeate fraction along with the native whey proteins. So if we want to use this cold microfiltration permeate then in the manufacture of infant nutrition products, it is enriched in beta casein. It is selectively enriched in beta casein, as you can see from the chromatograms on the next slide. But of course, the whey protein profile is unaltered. Okay, so we still haven't enriched the alpha-lac component. We've just stripped out native whey proteins in the same ratio as they were present in milk originally. And you can see that in the chromatograms on the next slide. And a lot of that work that we've done in comparing, the performance of membranes with different porosities and their impact on protein fractionation at low temperature from skim milk has been published in this paper in the International Dairy Journal, which is shown on the next slide if anybody wants further information on that. And maybe for people from an operations perspective as well, there's a lot of information in that particular paper on fouling and membrane resistance and processing performance of those membranes as well, as affected by temperature and by the fractionation of the major protein fractions in skim. So I've mentioned that this cold microfiltration permeate is an interesting material to start making infant nutrition products from. Clearly, one of the challenges with it is that it's quite high in minerals, so the mineral to protein ratio is quite high. So that needs to be brought down. The proteins need to be enriched in that stream. But as you can see from the next slide there, entitled Purification of Beta Casein from Ideal Whey, if we take that clear cold microfiltration permeate and we heat it to temperatures as gentle as just over 10 degrees Celsius, it actually destabilizes and precipitates. And you can see on the far right hand side that precipitate is actually pure beta casein. Okay, so you can generate high purity, high recovery beta casein fraction from this approach. But again, I guess we come back to the earlier point. One of the limitations with that approach is that the beta casein is insoluble, and it would need to be converted to a soluble form for various functional applications later. So what we wanted to do was to be able to recover that beta casein in a soluble functional form without precipitating it, essentially. And the process we arrived at to do that essentially involved demineralizing that cold microfiltration permeate using extensive ultrafiltration and diafiltration to wash out the minerals, no different to what we would do in making an MPC or a WPC, but then to form micelles in a controlled fashion from the beta casein. So by warming of the demineralized cold microfiltration permeate, it was possible to get the beta casein to form micelles, which were stable. And of course, these micelles then, compared to the whey protein monomers, the micelles are quite big. And it's possible to separate the beta casein micelles from the monomeric whey proteins using the same microfiltration membranes as were used originally to strip out the beta casein from the skim milk. So it's quite an interesting process in the sense that it uses the same microfiltration hardware in both phases of the process, both stages of the process, but the chemistry of the proteins is manipulated to change the size and the selectivity of the proteins during filtration. And the streams that are generated from that then are, a beta casein concentrate, which is called BCC on the slide there. So that's just a protein fraction specifically enriched in beta casein. The side stream of that then is serum proteins or native whey proteins, which can be further processed to produce, WPCs or WPIs based on native whey. And the other side stream from earlier in the process is what we call, it's basically micellar casein concentrate, but it's slightly depleted in beta casein. So it's a beta casein depleted micellar casein concentrate. And one of the key differentiators with this process is that all of the side streams and all of the products are maintained in a soluble form throughout processing with important functionality applications. So just the next slide gives a little bit more detail on the demineralization process. The objective here was to reduce the calcium content, and because calcium on heating clearly drives aggregation of the beta casein molecules, and that's something we didn't want because it would lead to precipitation. So by demineralizing the cold microfiltration permeate and bringing the calcium content down sufficiently, it was possible to be able to form micelles from the beta casein fraction then. And you can see that on the next slide, where it shows the thermoreversible micellization of beta casein in that microfiltration permeate. Okay, so in the middle image there, you can see the white turbid appearance to the solution, which is caused by the beta casein micelles. So these are big enough then to be able to physically separate them from the whey proteins using the same microfiltration membrane. And when that solution is cool, then it reverts back to being a clear solution. So temperature is critically important in driving that micellization process, but we didn't want it to become uncontrolled in the presence of calcium. There's a couple of slides after this which give a little bit more detail. I'm just going to go through them very, very quickly, but if people have, because I'm conscious of time, but if people have questions, obviously, and I see there's one has popped up already, please do continue to populate them in the chat box, and we'll come to them in a few minutes at the end. One of the things that's important for controlling this micellization process is ionic strength and controlling ionic strength. And we did quite a bit of work in this area, as you can see on the next slide, where we basically changed the ionic strength of the diafiltration medium by blending water and milk permeate. And essentially what that showed was that is increasing slightly the ionic strength of the diafiltration medium helped to improve the yield and the purity of the beta casein. So it reduced the losses of beta casein to the permeate fraction, so reduced the amount of beta casein in the serum protein stream, and it thereby increased the recovery and the yield of beta casein in the beta casein concentrate. So ionic strength is critically important in this particular process. And that drives, the micellization process, the presence of calcium in combination with increased temperature, drives the micellization process. And we were able to monitor that using changes in particle size distribution of the micelles, which are shown on the next slide. And you can see some data shown on the right hand side of that slide for purity of the beta casein concentrate ingredients. So with the use of medium ionic strength microfiltration, the purity of beta casein increased and the losses of beta casein to the permeate fraction decreased. finally, then, it's slightly different, but just to mention it because it will be interesting to people in various applications, is that we did quite a bit of functional characterization of the beta-casein ingredient in different media, so in water and in milk ultrafiltrate or simulated milk ultrafiltrate as a function of temperature and cooling cycles and so on. And you can see on the next slide entitled Reconstituted Beta-casein Concentrate Powder, when we increase the temperature of a beta-casein solution in water, it does become turbid. And that's due to the formation of the micelles and so on. But in water, on cooling, that's completely reversible, okay, which is shown across the top of that slide. Whereas in SMUF, which is simulated milk ultrafiltrate, it does obviously become turbid, and it becomes turbid more quickly on heating in SMUF than in water. But the micellization process is not reversible, which is shown on the right hand side of that slide. So I suppose one of the interesting applications of this finding is that beta-casein in solution can help to stabilize minerals, particularly help to stabilize against the precipitation of calcium phosphate on heating. So that could have interesting applications in other types of nutritional products. Okay, so just into oops, gone one too far. Just to wrap up then, and to come back and mention one of the things we flagged at the outset, was that while we have spent quite a bit of time talking about beta-casein, we've also been doing quite a bit of work on modifying the whey protein profile of infant nutrition products. And the target here is to understand what happens during processing when the alpha-lac to beta-lac ratio is increased, because that's the overall objective, is to deplete beta-lac and enhance the levels of alpha-lac and lactoferrin if possible also. And just to give you a snapshot of some of the work we've been doing, the heat stability curves shown on the next slide, they basically show heat coagulation time on the y-axis as a function of pH for a range of model infant nutrition products. And these 5 formulas have the exact same total protein content, the same whey to casein ratio, and the same pH, same minerals, everything. The only thing that's different is the alpha-lac to beta-lac ratio. And you can see clearly there that as we increase the proportion of alpha-lac as a proportion of total whey protein, that the heat stability increases dramatically. Okay, so the heat stability increases, and the pH of maximum heat stability shifts slightly to the left as we add alpha-lac. So we would be adding alpha-lac to match the whey protein profile of human milk, but it also has important, in this case positive, technological implications around heat stability. So an improvement in heat stability would be expected to result in reduced viscosity during processing and improved processing performance, less fouling, etc. in the manufacture of infant nutrition products. And we've also done some work in looking at the importance of the medium, so whether it's water or SMUF or infant formula permeate, that's used for assessing and predicting the heat stability of ingredients for infant nutrition applications. And that's detailed in the research paper published in Separation and Purification Technology, which is shown on the next slide. So I'm conscious that there's some questions coming through. So just to wrap up then, and to pull together a few of the strands throughout the presentation. Obviously, we've shown that native whey, so that material recovered by microfiltration of milk, it's an interesting starting material for the production of infant formula protein-based ingredients. And by modifying that process with cold microfiltration, it's possible to enrich the beta-casein fraction. And further developments in modifying the beta-casein to whey protein, and in particular alpha-lac fractions, are possible to build on top of that, and that's some of the work that's ongoing at the moment. There are clearly challenges with the manufacture and processing stability of some of these ingredients, Particularly in the case of beta casein, it's not the most heat stable of ingredients, as we've seen from the earlier slides. We've used that to our advantage for the recovery of beta casein, but it may be a challenge in the manufacture of infant nutrition products enriched in beta casein. The micellar form of casein is particularly heat stable, and moving away from that generally decreases the heat stability. The other thing is that all of the streams that we've generated are soluble, and as a result are functional. And we've actually done some work on some of the beta casein depleted micellar casein concentrates as well in cheese applications and in powder applications, and we've seen some interesting benefits in terms of functionality there as well. And just the final point then we went through there was the improvement in heat stability on increasing alpha-lactam to beta-lac ratio. So all of these protein fractions can be evaluated and are being evaluated in model infant nutrition products. Okay, so I think that brings us to the end of the presentation. So and I see there's a few questions after popping up on the screen as well. Can you see those there, Alan?
I can, yeah. Thanks, James. We're happy
so I was just looking at the
questions.
So will we
the question and then answer it? That'll be great.
Using membranes before separation of beta casein considered, and does that simplify getting pure beta casein after microfiltration? Okay, so that question relates to the sequence of addition. So removal of whey proteins using membranes before separation. Yes, that is something that has been looked at, and there are one or two publications and patents in that space. One of the challenges with it is that it adds additional processing complexity, and it actually tends to reduce the yield of beta casein quite substantially. But the advantage of it is that it generally results in a purer whey protein fraction. So if you're just interested in the whey proteins, then it's easier to generate a pure whey protein fraction, not contaminated in inverted commas with beta casein, but the yield of beta casein suffers. So there's two. We don't have the time to go into it today, but there's two quite different approaches that can be taken here. And one is the cold followed by the warm process, which is what we've outlined, whereas the alternative is to use a warm process followed by...
Your question from Manny just further up. During MF, when beta casein is removed from the permeate, doesn't more beta casein leave the micelle to maintain equilibrium?
Okay, so it is an equilibrium. So as you remove beta casein, then certainly more beta casein will enter the serum phase of the milk. But typically that's a slower process than the time frames that apply during membrane filtration. So the key there is actually time of holding prior to microfiltration. And generally you're talking about several hours of cold storage being required to maximize the release of beta casein into the serum phase.
There was a question there about the heat stability. I can take that if you like, about whether, from Jared, about whether the heat stability changes due to the heat denaturation temperature. The heat stability was done at 140 degrees, so it's going to be way above the temperature. But it's the fundamental reactivity of the beta-lactic globulin and the alpha-lactalbumin being very different, and the heat stability being very dependent on the interaction of beta-lactic globulin with kappa casein. So removing or reducing the beta-lactic globulin completely fundamentally shifts the mechanism by which the proteins are interacting. And basically, the less beta-lac you have, the less destabilizing influence, the more stable overall the formulation is going to be. So I guess that's one good thing about reducing the beta-lac. Unless, Seamus, you want to add anything to that?
Yeah, no, absolutely. I suppose the heat stability test is an endpoint destructive test, and a lot of what we do, in mapping the performance of these ingredients in the process would involve measuring viscosity, for example, throughout simulated processing as well. So yeah, another question I see there is, could you suggest possible uses for the byproduct, so milk from which beta casein has been removed? And that's an important question because I mentioned earlier that one of our objectives at the outset was to maintain all the streams in a soluble format, and there is quite a volume of beta casein depleted micellar casein concentrate produced in this process. And some of the applications we've looked at center around cheese applications. Hopefully everybody can hear me. I'm getting a lot of feedback on the microphone here. Oh, that's better now. So for cheese applications, for example, we have looked at meltability of cheese made from beta casein depleted milk, and it's actually enhanced. And we've also looked at renocoagulation properties of the beta casein depleted material, and generally what we find is herd cells having formed slightly.
A1 and A2 milk, we haven't done.
Yeah.
We haven't got A1 and A2. Hasn't been a particular feature of the it isn't a significant topic, at least in Ireland, the comparison of the two. So we haven't done any work on A1 versus A2. But if there are, I wasn't aware that there were differences in micellization properties. But it could be an interesting thing to have a look at from a scientific perspective, but it hadn't crossed our radar. Certainly mine anyway, Seamus. I don't know if you have any comments on A1 versus A2 in this context.
The same here, but if there are, as I say, if there are differences in micellization, then it would be interesting. I think we've covered all of Manny's questions, but there was one from Jared, and that was, if you were starting from scratch in terms of a starting material, would you choose bovine milk? Or if not, what commercially available mammalian milk would be a better starting material? And clearly, I guess, in this case, the interest would be in any commercially available milks that have higher levels of alpha-lac, lower levels of beta-lac, and possibly higher levels of beta-casein to start with would make it easier, essentially. And there has been, not on using microfiltration, but there is quite a bit of interest in goat's milk, for example, for the manufacture of infant nutrition products where the protein profiles will be different. But they would be the guiding principles, so higher beta-casein as a percentage of total casein and higher alpha-lac to beta-lac ratios. So any milk that has those features would be an interesting starting material.
Very good. I've got a couple. Tom, he's dropped off now, but he did ask. He understands trying to replicate the protein composition of human milk. However, not a lot of evidence or studies on the benefits of beta-casein and enrichment of IFFO. A lot of evidence on the whey, WHEY, ALAC and lactoferrin benefits. Do you have any examples of studies completed on the benefits of replicating beta-casein in content?
Yeah, he's right. It is a challenge because when you look at the caseins and the amino acid profile and so on of the caseins, there aren't much differences between any of the caseins. The one that stands out with beta casein is a high content of proline, specific amino acid, and I think indirectly what that results in is improved digestibility and altered curd forming properties. So a lot of the benefits associated with beta casein are almost indirect. It forms a softer curd. It's easier to digest, reduced, gastrointestinal difficulties, etc. As a result.
Right. Okay.
Whereas the nutritional implications of modifying the whey protein profile are easier to support with clinical data. Particularly alpha-lactalbumin, has been shown to improve gastrointestinal tolerance and modifies sleep behavior and so on.
Right.
Whereas it is a bit more challenging with beta casein.
Wow. Okay, and are there any examples of beta-casein enriched IFFO currently on the market?
There are,
Yeah.
but we couldn't possibly say.
Right. Okay. I'll leave that. I might send this email on, and you can answer it. And what are the potential applications and benefits for the retentate from cold MF process?
Yeah. So one is the improved meltability and improved heat-induced functionality of cheese. Because beta casein is quite hydrophobic, and on heating it tends to associate. So removing some of it from the starting material for making cheese has been shown to improve meltability, and that's some work we did between UCC and Madison. And the other thing that we've seen more recently is improved solubility and rehydration of the resulting milk protein concentrate powders.